floor is yours.
Okay, great. Thank you so much for this invitation. So this project is joint with kind of an eclectic team. So this is Isaiah Andrews, Drew Fudenberg, Li Hualei, Xiaofeng Wu, and myself. So there is econometricians, economic theorists, statistician, computer scientist, and I think you'll see that the question we're looking at is very much at the intersection of these areas. All right. So when we train a model on data, we often hope that that model is going to be useful, not just in the specific domain from which the data was drawn, but also hopefully in other related domains as well. Okay, so just to give you a concrete example, and this is one we're going to be looking at again later. Suppose we have a data set consisting of evaluations of risky lotteries made by subjects in the United States. And we can take that data set and use it to estimate a model of risk preferences. Okay, but we might hope that that model is going to be useful not just for predicting future evaluations of risky lotteries made by subjects in the United States, but also hopefully sort of related data, right? So for example, evaluations of risky lotteries made by subjects in Germany. Okay, now whether this estimated model of risk preferences is going to be useful for helping us to predict these evaluations is going to depend on whether this model that we've estimated, in fact, captures generalizable structure that's shared across these different domains. Okay. Now, we think this question of generalizability or transferability is especially interesting right now because of the increased use of black box algorithms within economics. Right, so this place where I had initially put an economic model, we can simply replace that with a black box. Right, I can train a black box algorithm on the same US data, and I can ask the same question of whether that trained black box algorithm will help me to predict this German data. Okay. Now, what the distinction is precisely between economic models and black boxes, I'm not going to offer you a formal definition. So the way that we think about it is whether the structure or architecture of the model is precisely tailored to the domain that you're interested in. Okay, so for example, this is a depiction of CPT, cumulative prospect theory, which is a popular model in behavioral economics for risk preferences. And it has a very clear narrative, right? So the idea is there's a value function over money. It takes a particular shape. Also, people misperceive probabilities, and there is a specific probability misperception function, right, taking a specific shape. So this is really a model of perception of risk. Right now, in contrast, if we turn to a classic black box algorithm, so this is a depiction of a random forest. It's a collection of decision trees. Okay, so you can estimate this model, you can train it for predicting evaluations of risky lotteries, but you can use this very same architecture for classifying images. So there's a sense in which this architecture is really not tailored to the specific setting that we're interested in. It's sort of across, very unrelated domains, right? So that's how we're going to be thinking about this distinction. But in the talk, we're going to look at specific black box algorithms and specific economic models. Okay, so which of economic models or black boxes should we expect to transfer better? And I think that question is actually not obvious ex ante. So black box models have been widely criticized for their lack of generalizability. And certainly many economists believe that the value of economic models is that they're capturing structure that is in fact general and apply across different kinds of domains. Right, so these are just some example references making this point. Okay, but on the other hand, economic models have also been criticized for their lack of generalizability. In particular, many claim or argue. In fact, I think we would all agree, right, that economic models are oversimplified descriptions of reality. We're not trying to literally capture what's going on. And as a result, some people have taken the view recently that large data sets and flexible black box methods might in fact help us to discover new regularities that are not yet captured within these economic models. Okay, so from that point of view, we might actually imagine that black box algorithms would be able to transfer better by capturing new regularities, right? So the idea is that this structure that the economic model is describing may be real, but maybe there's additional things going on, right? Maybe it's not just probability misperception. And if this algorithm is sufficiently flexible, potentially this flexible algorithm can actually capture some of those additional behavioral phenomena or other kinds of regularities that are present in this domain. Okay, so this paper has two contributions. So first, we're going to model this transfer prediction problem, and we're going to provide confidence intervals for the transfer performance of a given model. And then what we're going to do is we're going to apply these methods to understand in at least one application, and it's going to be the one you've already seen with risk preferences. We're going to understand in that application whether, in fact, economic models generalize better or black box algorithms do. Okay, so just a quick look at the related literature. So within economics, there's a large literature on meta-analysis. The main difference here is that that literature has focused on parameter variability, right? So you're estimating, let's say, a risk preference. How much does that estimate vary across the different domains? We're going to be looking instead at the variability of the performance of a given model. And those two things are related, but not the same. Also, there's a recent literature that's been comparing the predictive performance of black boxes to economic models. These comparisons are almost always within domain, meaning we're fixing a given setting. We're using some data from that setting to train and some data from that setting to test the model. Here, we're going to be importantly interested in this across domain problem. So Christoph has a nice paper which is looking at a rail transfer prediction problem. So to the best of my understanding, I think in that paper, you're looking at a comparison of different economic models, not a comparison of economic models and black boxes. But I think it actually would be cool to take that data and actually do a comparison across these different kinds of predictions. Okay, so in computer science, there's a literature on domain generalization, which is very related. The main difference here is going to be in goals. So the CS literature is primarily focused on developing algorithms that are going to achieve good out-of-domain generalization in practice. And in contrast, we're going to say, you give us a model. We don't care if that's the best possible model, but we want to give you a confidence interval for a guarantee for how this model is going to do out of domain. Okay, and then finally, we're going to be building on ideas from the recent conformal inference literature in statistics, okay, to prove some of the results. All right, so are there any questions about the high level of what we're trying to do? Okay, if not, let's just dive straight into the framework. Okay, so first, some foundations, right? So for us, as usual, a sample is going to be a set of observations, xi, yi, drawn IID from some joint distribution. Okay, so we're going to interpret this xi as a feature vector or a covariate vector. We're interpreting yi as the outcome that you would like to predict. Okay, so this is an example sample. Okay. Now, the standard out-of-sample test for a model looks like this. So what you would do is you would take your sample, you would break it into two parts. Okay, one part we'll call the training data, and you would use that part of the data to estimate the free parameters of your model. Okay, the remaining part of the sample we would call the test data, and we would take the model that we've estimated in the first part, use that to predict the outcomes given the features in the test data. Okay. Why do you do that? Well, you do that because the performance of the model on this test data is going to be informative about the performance of this model on a new unseen sample of observations, again, importantly, drawn from the same joint distribution, P. Okay, so this is the classic out-of-sample test. Right. Now, that's interesting in many settings, but sometimes what we actually want to know is not how well the model will perform on new data from the same distribution, but rather new data drawn from a different distribution. Okay, for example, we might again have our US data constituting one sample. We might have our German data constituting a different sample. And we might think that the observations across these samples are actually drawn from different distributions. Right. So within the US data, they're drawn IID from some distribution P1. But within the German sample, they're drawn IID from a different distribution of P2. Okay, and we might ask, well, what happens if we take the US data for training, the German data for testing? Can we use the performance of this model on this new domain to provide confidence bounds for the estimated model's performance on yet a new unseen domain, right? Very much an analogy to the standard out-of-sample test, but now replacing observations with samples. Okay, so this problem is going to be hopeless unless we place some assumptions on how the distributions are related. And largely the computer science literature has worked with assumptions that limit how different these distributions P1 and P2 can be. Okay, so we're going to take a slightly different approach here, again, building more on the conformal inference literature. And what we're going to suppose is the following. We're going to suppose that there is a meta distribution mu, which is a distribution over joint distributions and sample sizes. And we're going to suppose that each sample SD, right, so this might be the US data or the German data, for example, each sample SD is generated by first independently drawing a joint distribution and a sample size from this meta distribution mu, and then generating MD observations, whatever that sample size is realized to be. We're going to generate that many observations IID from the realized joint distribution. All right, and as shorthand for this process, we're simply going to say that the samples S1, S2, so forth are drawn IID from this mu. Okay, are there any questions about this slide? Because this is really these are the substantive assumptions right here. Okay, good. All right, so we're going to suppose that the analyst has access to metadata, which is going to be samples S1 through Sn, which are generated independently in the way that I just described. Right, so we might have, each of these is a sample. They might have different numbers of observations, but again, importantly, what's different is that the distribution governing the samples are different, but themselves drawn IID. All right, and what we're going to be interested in is the performance of a model on a new unseen sample generated in the same way. Right, so again, just to be clear, we're going to suppose that the analyst observes S1 through Sn. There's going to be some new Sn plus 1, which you don't get to observe, and we want to be able to forecast how well the model is going to do on that new sample. Right, so that's just this question. Yes, please. Yeah.
So the question is like, okay, how? So
I think cut out. Just do you mind just repeating what you just said? You cut out for a moment for me.
Sorry. How do you interpret this IID?
Yeah. No. Great. Absolutely. So that's the the main substantive assumption, and it's what's nice about it is it's going to allow us a lot of freedom not to impose specific assumptions on the distributions themselves. On the other hand, it is a very strong assumption. So you essentially have to be thinking that these settings are symmetric, right? That there's ex ante, not not anything different about the samples that we've already gained access to versus the sample, what we're interested in, right? If you think about these as different experiments, let's say data from different experiments, then if the experiments are run at n different locations, we're thinking that the n plus 1 location is a different location, but somehow not chosen or selected in a different way from the n locations we've already seen. So we actually do have an extension of our results where the IID assumption fails. And unfortunately, I'm not going to be able to talk about that here, just because this is relatively short. But I guess I don't want you to think about that assumption as too critical here. Okay, if we can bound the extent to which it fails, then we can also generalize the results.
Annie, could you get away with exchangeability instead of an IID?
Yes, absolutely. Yeah, everything in fact that I'm going to tell you today goes through with exchangeability. Okay, great questions. All right. Good. Okay, so I've been talking about the performance of the model. What do I mean by that? And here the talk would be pretty reduced form. I'm not going to introduce a loss function or anything like that because it's really actually not going to matter for the results. All we really need is notation for what I'm going to call the transfer error from a set of training domains to a test domain. Okay, so in more detail, let's imagine fixing a model. Again, that could be an economic model or a black box. We're going to fix a subset of the training samples. All right, so a subset of 1 through n. And we're going to fix another sample to be our test sample. All right, so for any t and any d chosen in this way, I'm going to let E subscript TD denote the transfer error when we train our model on the samples indexed to t, but then we test on the sample indexed to d. Right, so for example, I might choose the American and Bulgarian data for training. So then my training set would be this one here. I might choose the Chinese data for testing. Okay, so my test set is d is equal to 3. And then this notation simply means the error that I get when I estimate the free parameters of my model on this data and test that estimated model by making predictions on this data. All right, so to develop these confidence guarantees, it's going to be useful not to in fact use the entirety of the metadata for training, but rather to use a strict subset of the data. So what we're going to do is we're going to fix a number R, which is going to be the number of samples we're using for training. And we could pick some R of these samples and just work with that, right? Like I could say, let's really just train on the American and Bulgarian data if R is equal to 2. And see what happens there. But in a sense, that privileges the American and Bulgarian data. It says there's something special about that data. the guarantees that I would be getting then would be for the specific rule that's trained on those two countries, right? And because we've actually assumed this symmetry across samples, in a sense, that choice would feel rather arbitrary. So what we're going to do instead is we're going to choose these R training samples uniformly at random from all subsets of 1 through n of size R. Right, so if R is equal to 2, right, we might be training here, we might be training here, so on. Okay, I'm going to let T tilde denote the random set of training domains, which is drawn in the way that I just described. Right, so it's going to be drawn uniformly at random from all subsets of 1 through n of this fixed size R. And then the quantity that we'd like to provide a confidence interval for is this one here. So this is the transfer error that we get when we train on this random set of training domains. And then we test on the new unseen target sample Sn plus 1. Right, and then just to remind you, what we mean by this confidence interval is we're looking for an interval that is a function of this metadata with the property that the probability that the quantity we're interested in falls within this interval is at least some 1 minus alpha. Okay, are there any questions about our definition of this quantity, what we're looking to study?
I have a question, if I may.
Yeah, go.
So are you interested in a particular characteristic of that data? I mean, or is it just an overall fit in some sense, or so are you going to look at a sufficient statistic, like you're estimating a proportion or a mean or something, or so where
of this quantity?
Yeah, or can it be anything?
Yeah, okay, great question. So so the result that I'm going to show you is providing a forecast interval or confidence interval. We call them forecast intervals in the paper. Is providing a confidence interval for this quantity. So the actual transfer error itself, right? And actually, the reason we call them forecast intervals and not confidence intervals in the paper is because this quantity is actually random, right? It's going to be random because, this T tilde is randomly determined, right, from all possible subsets of size R. So in a sense, these confidence intervals are going to have the strange property that they're actually not going to shrink as the total number of domains grows large, because there's fundamental randomness in what this quantity is, depending on what the realization of this quantity is. So, so in the paper, we actually provide confidence intervals for other statistics of the distribution of this quantity. Right, so we provide confidence intervals for quantiles of the distribution of this transfer error, and we also provide confidence intervals for the expected value of this quantity. Right, was that the question?
I mean, I think close, but I mean, so I was just wondering, so I mean, for example, I had in mind a setting where every country is just a probability of producing heads for a coin.
Okay.
Right? And then you have, and then you're looking at a new country where you have a new probability of creating heads for a coin. And then I'm just interested in the proportion, let's say, right? So then there would be a very specific statistic that I would be interested in. And I was just trying to see whether this E T tilde thing is that statistic, the proportion, or would it be something more general about the
I see. Okay, so that's interesting. So you're trying to learn from these samples something about. So yeah, it's not clear to me that what you just said would map into this, right? So for us, it'd be more like, okay, so these are probabilities of heads. So if each sample is just heads and tails, right?
Yeah.
We would be using those samples to estimate a probability of heads or tails, and then using that to make predictions for heads or tails in the new sample, and then looking at the error of that that way of making predictions. But it's not. This is not, I actually have to think about it, whether we actually could extend our results for what you're looking at, but at least, so far what we've been thinking about, this is not a statistic of the sample itself. It's a property of the model that we've estimated from the training samples and how that model relates to the new sample.
Okay.
All right, so let me jump into the method and results. Okay, so as we said, we're training on R samples. And remember, we don't get to see this one here. We do get to see S1 through Sn. So the way we're going to construct our confidence interval is by looking at all possible choices of R training samples and one testing sample from the metadata. Right, so for example, if R is equal to 1, I might take my American data for training, my Bulgarian data for testing. Might do this, might do this, might do this. Right, and in this way, I'm going to get a large pooled sample of transfer errors that I actually get to observe. Okay, if R is equal to 1, we can in fact represent these transfer errors in a matrix like this, right? These are my n samples that I've observed in the rows and the columns. Depending on which one I use for training and which one I use for testing, I'm going to get a different transfer error. And what I can do is I can take this pooled sample of observed transfer errors and let E tau denote the tauth quantile of that pooled sample. Right, and then what our main result says is that those quantiles are going to allow us to construct valid confidence intervals. And this is actually a typo here. That should be 1 minus tau. I changed the notation slightly from the paper. Okay, so let me just say it in words correctly, according to the notation we've been working with so far. Or we're working with this is like upper and lower quantiles. These are sort of details I'm ignoring here today. So this is a one-sided confidence interval, right? So this is taking the tauth quantile of the pooled sample. And this is saying the probability that the quantity we're interested in is less than this tauth quantile of the pooled samples is at least the right-hand side. And this is a two-sided confidence interval. So this is saying if I take the tauth quantile, put that as my upper bound, the 1 minus tauth, so that's the error here. If this is the 1 minus tauth quantile as my lower bound, then the probability that the quantity belongs to this interval is at least the right-hand side here. All right, so let me just, how am I doing on time? Still pretty good, right? Okay, so let me quickly.
Sorry, you are 23 minutes in. So
okay, yeah, so
time.
Okay, good. So let me just walk through how we showed this result. Okay, so by assumption, the samples are exchangeable. Okay, that's really the key driving force here. And just to remind you of the definition there. So if I take my samples and I permute the indices, right, these are going to share the same distribution. And what that means is if I go back to this matrix of transfer errors that we've already looked at, and now I've just added in the n+1th sample, right? In a sense, these labels aren't particularly meaningful, right? If I were just to tell you what the pooled sample of transfer errors was, without telling you the labels that they came for, right? I take all these transfer errors, I put them into a bag, shape them up, right? Give that to you. You can essentially view this quantity that we're interested in as a uniform draw from that sample, just a draw from this anonymous bag. Right, and what that means is that if we now take E tau star to be the tauth quantile of this pooled sample of transfer errors, okay, then essentially by definition of the quantile, the probability that this quantity that we're interested in is less than this tauth quantile is going to be at least tau. Right. Now, the catch here is that we don't actually observe that whole matrix, right? We don't observe the transfer errors that correspond to the unseen domain n+1. This is what we get from our metadata. And what we've defined our E tau to be actually is the tauth quantile of this pooled sample. Right. And so essentially it's a counting problem. Right, what we would like to understand is what is the probability that a randomly drawn cell from this larger matrix, including n+1, so if I draw a yellow or blue cell uniformly at random, what is the probability that that realized value is going to fall below the tauth quantile of the yellow cells? And that you can show to be this quantity here. So this is tau times n choose r+1 divided by n+1 choose r+1. That returns this quantity here. And this quantity is precisely the quantity that we saw in the one-sided confidence interval. Okay, there's one final detail here, which is that we're conditioning on the realization of the samples, but you can use the law of iterated expectations to get rid of that. So then we still have the same quantity. All right, so that gives us the one-sided confidence interval, and the same sort of argument delivers the two-sided. And this is the only result I'll show in this talk, but let me just quickly mention some other results we have in the paper. Right, so again, this is for the actual realized value of the forecast interval itself. where again, remember this quantity is random. So this was in the conversation with Christoph. So T tilde is a random variable. So this quantity is random. So even if you take n to be to grow large, right, these intervals aren't going to shrink to a singleton the way that you might expect usual confidence intervals to do, right? So on the other hand, if we look at statistics of the distribution of the transfer error, then we can develop more standard confidence intervals that do vanish. So for example, you might be interested in the median of the transfer error, or you might be interested in its expectation. And we provide confidence intervals for these quantities. And then finally, I've also mentioned this in a previous with a previous question. So we also have a generalization of this result for what happens when the IID assumption fails, but the extent to which it fails can be bounded. All right, any questions about the results?
Annie, so
Yeah.
you seem to be saying you pick one population to calibrate the model, then you test it on one other population, and then you try it out on something, an unseen population. Can you optimize over the first part of that, the number of populations that you train the model on and the number that you tested on?
Yeah, that's a great question. So that effectively, you're asking, is there an optimal choice of R here, right? So remember, N is our total number of metadata, R is the amount we're using for training. Yeah. So we don't have any results to that effect. So it's, it's not clear, right? Because on the one hand, if you use more samples for training, you're probably going to get a better model. But on the other hand, you're going to have fewer samples for testing. So the confidence intervals are going to be worse. Right. So yeah, so there's that inherent trade-off. Yeah, I think that would be a super interesting question to look up in follow-up work. It's not something we've investigated here. Yeah. Okay, any other questions?
I have a question about T tilde.
Mm-hmm. Yeah.
There is a subtle way in it in which it itself depends on R, right? And
yes,
I
absolutely.
assume some sort of monotonicity, maybe, that the larger my R is, the more accurate my training is.
Well,
no?
so that's related to Arthur's question, right? Yeah. So yeah, so the larger your R is, yeah, exactly. The model, you're training it on more data. So in a sense, you might expect it's okay, for example, we might expect the distribution of transfer errors on the target domain to shift down in an FOSD sense, let's say, right? But to actually assess to provide a confidence interval for that error, right? You now have fewer samples in your metadata to actually test this model on.
Right.
So I agree with you that we should probably expect that model to be more accurate, but on the other hand, we're going to be able to say less about its accuracy.
Fascinating. Thank you.
Can I ask one more question? So if it holds you up too much, then delay it to later. But could I see again the definition of the transfer error? I still don't quite understand what it is.
Yeah, well, that makes sense because I didn't define it in great detail. So let's see. This is the slide that I had. Here it is.
Okay.
Yeah, so in fact, our results are actually going to hold quite generally. So, we're motivated in this paper by thinking about transferability. So this is, transfer error is what we think about primarily. But the results hold for any random variable, which is a function of the samples on which you're testing, training, the sample on which you're testing, and then possibly some additional randomness. So that's actually a very broad class. And, that's why I thought your question was intriguing, because I'd have to think a little bit about whether that class actually includes things like what you had.
Okay, but so the idea is a little bit that there's some sort of prediction in some sense that you derive from one model, and then you try to predict for the other model, and then you're looking at the prediction error in some sense, for example? Or?
Yes. Yeah. Okay. So that's our most direct,
okay.
we're most directly interested in. Yeah.
Okay, thank you.
Is there symmetry in this matrix of ease then?
Not necessarily. Yeah, that's also an interesting question, right? But it could be that
you need some assumptions to make that, like the samples being identical size.
Yeah, right. Good. So different sizes would be yeah, it might be a part of this, but yeah, in general, like E21 does not have to be the same as E12.
So
Sorry, you cut out.
so this is for any random variable, you said.
Uh,
So, but do you impose any particular structure on the type of random variables that E could be?
so yeah, so no, essentially no, right? It's yeah, it's the class that it has to depend on the training sample, the test sample, but you can look at, yeah, we're not using any any special properties of how we've defined transfer error.
Great, thanks.
Actually, quickly going back to Peter's question, so another reason, right, we might not expect this to be symmetric is if one of these samples is fundamentally more predictable than the other, right? Imagine that one is just a constant and the other is noise around that constant. It might be that if you train on the noisy version, you still get the right mean, let's say, which is great for predicting the constant, but now your error is 0, and in the reverse direction, you have a pretty bad error.
But
Okay.
would that violate the IID?
Oh, no, it doesn't, right? Okay, so good. Actually, let me actually emphasize this, right? So the distributions are drawn IID, but the realized distributions can be super different, right? Remember, we haven't placed any assumptions. We didn't even require these distributions to have the same support. So, yeah, so we're definitely allowing for the case in which some of these samples end up, very predictable, and others end up, yeah, not so predictable.
Got it.
Great. Okay, so now let's go into the application where we're going to be able to use this result. So we're looking at a very classic prediction problem from economics. So here, X, our future vector, is going to be a description of a binary lottery. So it's the 2 possible prizes and their corresponding probabilities. And Y, which we would like to predict, is going to be a subject certainty equivalent for that lottery. Okay, to evaluate error, we're going to use mean squared error. So this is our prediction. This is the true certainty equivalent. All right, so our metadata is going to be a sample of 44 samples of reported certainty equivalents across different subject pools. And this is drawn from 14 papers. We basically just went through the literature and tried to find every paper that we could that had a data set of certainty equivalents. And so there's no correct way of defining domains, right? This is somebody asked about how to interpret the IID assumption early on. And really, what you think of as the domains is going to correspond very tightly to how you're interpreting this IID assumption. For us, we're going to take domains to be subject pools. So every sample is going to be from a different subject pool. Okay, so we might expect that models of risk preferences trained on data from certain subject pools will be predictive of data elicited from others, but imperfectly so, and we might want to understand the extent of that transferability. All right, we're going to consider 2 economic models and 2 black boxes. So one economic model is going to be expected utility theory with Cara preferences. We're going to call it EU. And a second model is going to be a popular 4-parameter specification of cumulative prospect theory. Okay, we're going to look at 2 black boxes, random forest and kernel ridge regression. All right, so CPT, I'm assuming everybody knows EU with Cara preferences, so I'm not going to have a slide about that, but so CPT, for those of you who haven't seen it before, it's essentially a fancy version of the expectation of the lottery, or the expected value of the lottery, where the value function is the one given here. So in the gain domain, so this is the dollar amount, this is the value of the dollar amount. Okay, in the gain domain, this is what's given here. In the loss domain, it's what's given here. There's 2 parameters, alpha and beta, governing the curvature of this value function in the gain and loss domain. Okay, and the part that's maybe more interesting is this probability weighting function. So the idea is that people don't correctly perceive the probabilities. P is the true probability. W of P is how the individual actually thinks about it. And again, that's going to take a specific functional form in this version of the model that we're estimating. So this delivers a curve that looks like this. So you're overweighting low probabilities, underweighting high probabilities. And so the utility then of a given binary lottery is going to be this expression here. So there's 4 free parameters, alpha, beta, delta, and gamma come from the weighting part. And these are the parameters we would be estimating on the training data. And then taking to the test sample already estimated, right? Okay, so let's first consider as a warm-up, okay, let's first consider the usual out-of-sample test where we're training and testing. Is that a hand or was that an accident?
No, this is a hand, sorry.
It's a hand, okay.
This is one thing
You're not
that's-
supposed to interrupt.
So
Yeah,
if I
go
may, but there's one thing. So these models they're not probability distributions, right? So I mean, they're not
That's
like,
right.
yeah.
Yeah, absolutely. So you could also, there's nothing about our approach that requires, it's just a little bit easier to think about. So if you wanted to predict the distribution, right, you would have to change the loss function, but that's completely fine. You could also look at models that actually predict a distribution of certainty equivalence.
Okay.
Does that make sense? Yeah.
So yeah, so that you have, I mean, because I'm sure people will be inconsistent somewhat, right? And so there's noise in the data, which this model doesn't have, right?
Absolutely, yeah. So as a result, we're not going to expect a zero error to be possible here.
Okay.
So that, you know, even the best possible error is going to be something strictly positive in these settings, right? Because for the same lottery, two people might give different answers.
Okay, so in reality, you're sort of using a model plus a bit of noise in some sense for the distribution.
No. So our prediction, we're essentially trying to learn the expectation for each lottery, right? That's going to be the best possible prediction. So we're taking from each of these models a deterministic prediction of Y, and then we're evaluating it using this mean squared error. You could sort of rerun all of our machinery using, let's say, like a CPT with logit noise if you wanted to. But in that case, you would use a different loss function here to evaluate it.
Okay, thank you.
No problem.
Sorry, can you say, okay, what the covariates are in this situation?
Yeah, so the covariates are very straightforward. It's just this. Just the description of the lottery. All right, so let's first consider this usual out-of-sample test. So there's no transfer going on, right? We're training and testing on data from the same subject pool. And if we do that, so now we can do 44 out-of-sample tests corresponding to the 44 subject pools. And what we find is that the black box's out-of-sample error is slightly lower than the economic model's out-of-sample error for most of our subject pools. They're actually very close, but the black box does slightly better most of the time. Okay. Now, there's a couple of reasons that could be the case. Right. One possibility is that the black box is indeed learning generalizable structure that the economic models miss. Another different explanation is that the gains that the black box is making are specific to this within domain out of sample test. Okay, but that the structure that you're learning is not actually structure that's general and shared across the domains. Right, so to separate these, we can look at transfer performance. And so here, this is where we're going to apply our main results. So just to remind you, okay, good, now it's correctly stated. So if we look at this interval, which is the 1 minus tauth and tauth quantile of the observed transfer errors across different samples in our metadata, that's going to constitute a confidence interval with this guarantee for the transfer error on the new target sample. And so there's a couple of parameters here. So first, n is just the total number of samples in the metadata. For us, that's 44. And then there's a couple of choice variables, right? So R is one we've already discussed. It's a number of samples used for training. And then also tau is a choice variable, right? So every choice of tau is going to give you a different confidence interval. There's just a trade-off between the width of the confidence interval and the guarantee that you get. Okay, so wider confidence intervals with better guarantees, or you could have a more precise interval with a worse guarantee. Okay, so for our application, we're going to set R to be equal to 1 and tau to be equal to 0.95. And that's going to allow us to answer this question. So if I were to draw one domain at random, estimate my model on that domain, and then use it for predicting in a new domain, what is an 81% confidence interval for how well I can do, or how well I will do? All right, and this is what we find. All right, so here are the economic models. All right, here are two black box models, random forest and kernel regression. So this is EU right here. And these are just different specifications of CPT where we've sort of turned off certain parameters. So the full 4-parameter specification is this one here. Okay, so the two economic models are very similar. The black boxes are also quite similar, but there's a clear contrast across economic models and black boxes, right? So the black box confidence intervals are substantially wider, and also notably their upper bounds are substantially higher, right? And again, this is despite they're very similar within domain errors, right? So remember when we were testing out of sample, when we're training on testing on data from the same subject pool, the black boxes are doing better than the economic models. Now we change this to a transfer task, and now they seem to be doing worse, right? So this is suggesting to us that the economic models are learning general structure indeed better than the black boxes do. Are there any questions about this, this slide? This is sort of the main results from the application. We'll talk quite a bit more about how to interpret this, but just, are there any questions about what is here, or what this means? All right. Okay. So a natural question is why, right? What is going on? And a very intuitive answer is that the black box is just overfitting, right? This is the usual intuition from the out of sample setting. We might think that what's going on is that the black box, in its flexibility, is learning idiosyncratic behaviors of each subject pool that don't in fact generalize across subject pools, right? So for example, suppose the training data is Chinese data. And let's suppose that Chinese subjects idiosyncratically really like the number 8. So anytime the number 8 appears in a lottery, you overvalue that lottery. Now, if that's the case, CPT and EU are not going to learn this regularity, right? That's not permitted in the structure of these models. But the black box methods can, right? So if we train that very flexible black box model on this data with this peculiarity, the black box is going to learn that regularity, which is going to allow it to make better predictions on future evaluations made by future Chinese subjects. Okay. On the other hand, if that's not a regularity that's shared across, let's say, if that's not true about the German data, then now we take that black box, use it to make predictions on the German data, it's actually going to do worse, right, than the economic models, which were not allowed to learn this regularity. So this is a very compelling narrative, and in fact, it's probably a part of what's going on, but we're convinced that this is not, in fact, the full story, okay? And this is why we think it's not the full story. So it turns out that one of the 14 experimental papers that we got data from is actually itself a meta-study. So that paper consisted of 30 samples across different countries. And one feature of that data is that they used exactly the same lotteries in each of these 30 countries. Right, so they just fixed a set of lotteries and went to 30 countries and elicited certainty equivalents for those same lotteries. And what we can do is we can actually just repeat our analysis, taking those 30 samples as our metadata. Right? And if we do that, this is what we find instead. These are the confidence intervals for the transfer performance. So here, these are the two black box models. They're virtually indistinguishable from the economic models. Right. So from this, the picture is that the black boxes are not doing worse, right? So if all that was going on is that the black boxes are overfitting, they're too flexible, we should have seen that in this data as well, right? So what's different about this data? This is our best attempt at clarifying, what we think is the main contrast. So recall that observations in different domains are governed by different joint distributions. Now, there's two main differences in which these distributions can be different across different domains. Okay, so one source of variation is variation in the conditional distribution of y given x. So at an extreme, it might be that, in fact, every domain has the same marginal distribution over features, right? But a different conditional distribution. In our setting, that would mean that you're drawing lotteries from the same distribution, but people in different countries have different reactions to the same lotteries, right? So they report different different distributions of certainty equivalents for those lotteries, and that's the sorts of variation in the that's what makes different domains different. In the computer science literature, this is often known as model shift. Okay, another kind of variation is variation in the marginal distribution, right? So it might be that, in fact, all subjects in different countries are the same. They respond to lotteries in the same way. They have the same distribution of certainty equivalents for those lotteries. Okay. But what's different across these different samples is that you're actually sampling different lotteries. Okay. For some reason, in China you get lotteries of a given form, and in Bulgaria you get lotteries in a different part of the lottery space, right? And in the CS literature, this is often known as covariate shift. Okay, so these are two different kinds of transfer problems, and they have different implications for the relative performance of black box algorithms versus economic models. Okay, so why? Consider the first kind, right? And again, at an extreme, you have these 30 samples that we just looked at, right? It's literally the same x's, but just different y's for those x's. So in this case, the transfer prediction problem is actually kind of not a particularly difficult transfer prediction problem in the sense that it doesn't actually require real extrapolation, right? If you think about actually just a table base, if you take those x's that appear in each of those 30 samples and you literally just memorize the expected value of y for each of those x's, that's going to be the best you can do for this transfer prediction problem, right? And if both the black box and the economic model can effectively learn the distribution of y's for the x's that actually appear, right, then these approaches are both going to do quite well in this kind of transfer prediction problem. In contrast, if it's really the x's that are changing, right, then you can't just memorize y's for x's you've seen before. You really have to be learning something from the x's that you've seen before about how to make predictions for new kinds of x's. Okay, that's a real extrapolation problem. And this is where it seems that the economic models are outperforming the black box algorithms. Right, any questions about what I've said here, right? So,
Yes, could I ask a question?
yes, please
Like
do.
the lucky number 8 we mentioned before, then how does this specific preference match into the two different cases? Is that the lucky number affects the probability, like the px, or is actually the conditional probability?
Good. Okay, so I would think of that as orthogonal. So this way of carving up transfer problems, I want to think about this as really like a separate explanation, right? So the thing about the lucky number 8, right? That's really just a point about overfitting. It's saying that if you overfit to what you've seen before and you don't have enough training samples, you might be fitting to noise. That's going to lead to worse predictions, both out of sample and out of domain. And that's going to be the case, I think, for both of these settings, right?
Okay, thank you.
Okay, yeah, thanks for the question.
So is there any hope of proving a general result along these lines?
Yeah, great question. So we don't have that result in this paper, but I do think that would be an interesting thing to look at, is formalizing this difference here, or formalizing how this difference has implications for the relative performance of black boxes and models.
I guess you need some kind of caricature of what the black boxes are doing in order to prove it.
Yeah, exactly, right. So that's part of the difficulty here, is right, like, you can prove a result for, let's say, the random forest algorithm, but in a sense that might not be so satisfying, right? So I guess that ideally you might have a result for a class of black box algorithms with a certain property. Yeah, so I think that would be interesting. We're just pointing out here that we think this is something that might be the case. Yeah, Christoph.
So you also have an interesting side result, right? That among all the economic models, they all seem to be doing equally well, reasonably, at least in this problem. So there's no reason to go to cumulative prospect theory over expected utility, it seems, in your data.
Yeah, that is true. I don't want to,
But only in terms of errors.
too much into that. Sorry.
Okay. Oh, only in terms of transferability, not in other terms.
Yeah. I mean, I guess one thing that's interesting also, so just in terms of transferability, and then also, I guess we're looking at a very specific kind of transferability here too, right? We're looking at transfer across the different subject pools. So I guess indeed what we're seeing is that for transferring across subject pools, there's not a big difference between EU and CPT. I think it would be super cool to look at transfer problems that are across domains that are a little bit further apart, and that's not something we're going to pursue here, but I think the machinery really could be used also. So, for example, you might be transferring across lotteries with different support sizes, right? Those could represent different domains, and then maybe EU and CPT would be more separated there, right? Or Christoph's paper was looking at transfer across different kinds of games. That's very much something you could also look at, right? So if you train on beauty contest games, now you make predictions in normal form games. And in that case, you might expect to see more distinction across. And in fact, actually, that is kind of what you did look at, right? So there were separations across the models in that case. So what you find this comparison in these confidence intervals is it really is indexed to a specific formulation of the transfer prediction problem. And I guess you couldn't even look at a meta problem where if you learn something about how well two models compare in certain kinds of transfer prediction problems, like can you make inferences about how well it'll do in a third kind of in a new kind of transfer prediction problem. But yeah, right. That's for the moment. That's purely just conjecture here. Okay, so what we found, these results are suggestive that block boxes transfer relatively worse when the feature vectors vary across the training and testing domains, right? And that property of how much variation there is across the X space is really critical for this the relative transfer performance of these two methods. All right, let me see how I'm doing on time. Okay, so I'm basically going to wrap up now. So also in the paper, so I've been talking about transfer error here. We've talked a bit more about how the results apply more generally. So in the paper, we actually also define two other measures. One we call transfer deterioration, one we call normalized transfer error. So normalized transfer error is a lot like transfer error. The difference is that we're normalizing by a proxy for the best achievable prediction in that domain. The reason being, again, that different samples might differ in how predictable they are. And so, you might see very large transfer errors for one test sample, just because that test sample is fundamentally unpredictable. It's not that your model is doing poorly, right? So you might want to hence normalize by some measure of how well you could possibly hope to do in that setting to keep these samples on level ground. Transfer deterioration is looking at a slightly different angle on the problem. So this is asking, how much do you lose by transferring parameters estimated from the training samples rather than by estimating parameters on data from the correct domain, right? So instead of transferring from American data to Bulgarian data, if I actually already had some Bulgarian data that I could train on, how much better would I subsequently do on testing on Bulgarian data? Okay, so all of the methods that I've shown you so far can be equally applied to these two measures. And in the application, we actually look at these as well, and the results are qualitatively similar to what I've shown you. Okay, so then just to conclude, so this paper suggests in one application and for one kind of transfer prediction problem that indeed economic models transfer better than black boxes. So there's still a lot of things left to understand. So model shifts versus covariate shifts is likely only one part of the story. We should also look at whether that holds up in other applications as well. We might ask, with enough data from different domains, is it the case that black boxes are going to win out again? Right. So here we're looking at one domain. And in fact, we actually repeated this analysis training on 3 domains instead of 1. And the results are qualitatively similar, but the black boxes start to do a little bit better. And then, the other side of this, so here we're not focused on developing the most generalizable model. We just want to compare off-the-shelf economic models with off-the-shelf black box algorithms, both of which are used in practice. But now, you might ask, suppose our goal is actually to predict as well as possible in the new domain, what is the best possible approach for this? And here, I think the answer is going to be something that's not purely black box or purely an economic model, but something that's really in between. And I think that's also exciting to consider what kinds of approaches might leverage both of these perspectives in a useful way. All right, so that's all I had, and I'm happy to switch to the discussion now.
Thank you very much, Annie. Let me kill the recording and we can proceed to a maximum of something like 20 minutes of discussion.